Okay, what we're going to talk about today are the actual functions for sine and cosine. Okay. And we're going to start out by looking at a graph on our calculator. Page 385, there's an exploration that we're going to look at. And we're going to simultaneously graph the unit circle along with the graph of the sine function. So to do that, we're going to make sure that we got a couple things correct in our calculator. If we go to our mode, and we make sure we're in radians. Anytime we graph the sine and cosine functions, we're going to need to be in radian mode. Okay. And the other thing we want to be in is parametric mode. We're not going to do a whole lot with parametric equations in this class. We will in calculus, but for the time being, we're just going to use it for our purpose of this exploration today. So we'll put it in parametric mode, and then also you should have a simultaneous mode as well. Okay. Sequential and simultaneous should be on there somewhere, depending on what calculator you have. Okay. And so if you're on all three of those modes and you hit y equals, okay, well, we're going to put in the y, or the x is cosine t, and y equals sine t. Okay, and this is actually the equation for the unit circle in parametric form. Okay, think about y. If I were to put in different t values here and take the sine and cosine, they're going to it's going to generate values that are going to be points on the unit circle. Okay? So remember, all the points on the unit circle are x equals cosine, y equals sine. Okay? So if I were to just graph that right now, that would give me a picture of the unit circle. Okay? And if I want to graph the sine function, I'm going to put a t in my x2, and I'm going to put sine t in my y2. Okay? So that's the setup that we need to have. Cosine t, sine t, that gives us the unit circle. And then the x2, y2 is going to give us the sine function. Okay? So we're actually going to see a picture of what the sine function would look like, and then we'll talk about why we get what we get. Okay. So with that said, let's make sure we get our window set up correctly. I'm going to go window. I'm going to go my t minimum. I'm going to go 0. I'm going to go 2 pi on my t max because I'm going to graph my sine function from 0 to 2 pi. The number that's on your t-step probably by default is something around that what I had there. If you don't have that number, type in pi divided by 24. Okay. Usually pi over 24 is a common t-step. And then x-wise, I'm going to put in negative pi over 2 for my x-men, just so I can see a little bit on the left-hand side. I'm going to put 2 pi on the right-hand side. My scale I have at pi over 2, you notice it's 1.57 again, that's pi over 2. And then my maximum, minimum in the y direction, I got negative 2.5 to 2.5. And scale of 1. All right. So what we're going to see then is that simultaneously, okay, the unit circle is going to get graphed, okay, along with the sine function. Now keep in mind that if I were to tell you to graph y equals sine theta on an xy coordinate plane, I want you to think about how we're going to get a graph of that. What are those values going to come from? Well, remember sine, okay, itself is defined, it's a circular function. We defined it by the unit circle. Okay, we know that if we were to put in theta values in here, okay, we would get out some kind of y values. And if we were to make a collection of these values, then we could certainly plot them on the xy plane, and we're going to get some curve. Fair? Okay. So, for instance, if I were to say 0, okay, and keep in mind that I'm working in radians here, so if I have 0 radians, okay, if I have 0 radians, that means that my function is going to be the sine of 0. Well, think about our unit circle in your mind. Here's our unit circle. If we're at 0, what's the sine coordinate there? The y coordinate at that point is what? This is our unit circle. What is the y coordinate at this point right here? It's 0. This is 1, 0 right here, isn't it? Around the unit circle. So that means 0, 0 is a point. I would plot that. Okay. And I'm just going to do a couple, and then we'll let the calculator show us the rest in a minute. So if I did another point, let's say pi over 4, for instance, would be a good one to use because we know the answer to that without having to do any work. The sine of pi over 4 we know is radical 2 over 2. So when I set up my tick marks here, I'm going to make my tick marks go by pi over 2's. Over to 2 pi here. And if I'm at pi over 4, I'm at radical 2 over 2, which we know is about 0.8 something. And I'm going to say my 1 is right here, so I can make the picture a little bit nicer. So I'm going to say that that's going to be right there, we'll say. If we put in a pi over 2, that means we're going to be at the top of the circle. So the y-coordinate at the top of the circle is 1. So we're going to be 1 there. Okay, and if we put 3 pi over 4, that's going to be right here. We know the sine coordinate there is going to be the y-coordinate. That's going to be positive radical 2 over 2 again. So at 3 pi over 4, we're going to be here. And then when we get down to pi, back over here, the y-coordinate now is 0 again. So we'd be at another 0 for this function. And what it boils down to is if we plotted a bunch of points in between here, okay, we would find that we have this smooth curve between 0 and pi. Okay, the sine curve looks like that when we plot all those points. Okay, so that said, let's go ahead and see what the calculator shows then, see if we see the same behavior then. Okay, and what the illustration here is that we're trying to show that as we go around the unit circle, okay, we're collecting y-coordinates from, because the sine is y, and we're plotting those y-coordinates on the coordinate plane according to this chart that we're making with the x being the independent variable and y being the dependent variable. So watch what happens when we got this. Okay. Okay. So notice as the unit circle plotted points around the unit circle, okay, the sine function went up to 1, down to 0, okay, and then it went down to -1 and back up to 0 again. Okay, and that right there that we see here is one cycle of the sine function. Okay, and then none of this is extremely new for us because we studied these functions in Algebra 2 also. But we're looking at it a little bit more in depth here in pre-calc and understanding, hopefully, okay, why does it have that shape? Okay, it has that shape because the coordinates of the unit circle, okay, generate the y-coordinates for the sine function. Fair enough? So let's see how that works for the second part. Okay, keeping in mind that when we're on the unit circle, just like you guys told me a few minutes ago, when we're on the unit circle, the sine coordinate is positive in the first and second quadrants. True? So notice, what's the graph like? The graph is above the x-axis. It's positive, isn't it? Okay. You said that in the third and fourth quadrants the sine was negative, so what should happen here? The sine function should be down here, shouldn't it? Okay, and if we plot points around the unit circle, and again I'm just picking some common points that we know. If I were to keep going with my chart here, and do 5 pi over 4 next, we know that's negative radical 2 over 2. We know that 3 pi over 2 is -1. We know that 7 pi over 4 is negative radical 2 over 2. And we know that back to 2 pi, same as 0, we're back to 0 again. So if we plot those points, okay, we would get the other half of that one cycle of that sine function. Now, the next question is, that is part of the graph, of course, but remember, how many times can we continue to go around the circle? Infinitely many times. So what's going to happen after we get here? So we're just going to repeat it. It's going to be, this is what we call a periodic function. Okay? It has a period, which means that at some point it starts over again, and it repeats itself. Okay? And think about why it repeats itself, because what do we know about coterminal angles? Okay? If we get back to this one, which would be 9 pi over 4, wouldn't it be the same as pi over 4? And we just plot the same set of y-coordinates over again, wouldn't we? Okay. Think about what's going to happen going left. If I were to go negative pi over 4, wouldn't that be down here on the unit circle? And wouldn't I get negative radical 2 over 2 again? -1, negative radical 2 over 2, back to 0. So going in both directions, we're going to get the same exact shape, and it's going to continue to repeat itself every 2 pi. Okay? And that pi, that 2 pi, we call a period. Okay? So that P, I'm going to write here, is called the period. All right. Questions so far? So if you remember, one of our when we studied our 12 families of functions at the beginning of this class, okay, sine and cosine were 2 of them out of the 12. Okay, and if you look on page 384, let's take a look at some of the facts, some of the analysis of the sine function here. If we have f of x equals sine x, domain is negative, or all real numbers here, negative infinity to infinity. The range is -1 to 1. The lowest we go is -1. The highest we go is 1. Okay, it is continuous. Okay, it's increasing and decreasing in periodic waves. So we're increasing, notice, from negative pi over 2 to pi over 2, decreasing from pi over 2 to 3 pi over 2. But if you think about it, wouldn't there be an infinite amount of ways that we could say that this is increasing? There's an infinite amount of spaces that's increasing. Okay, it is symmetric to the origin, so that means that the sine is an odd function. That means if we did sine of negative x, that would equal negative sine x. Okay. We do have an absolute minimum and a maximum here. 1 is the highest we go. Negative 1 is the lowest. There are no horizontal or vertical asymptotes. And the end behavior here, we say, does not exist because ultimately the function doesn't go to any particular number. It doesn't go to infinity. It doesn't go to negative infinity. It just continues to oscillate back and forth between negative 1 and 1. Okay. So therefore, we do not say that it has a limit at infinity or negative infinity. The end behavior of a sine function is that it oscillates between negative 1 and 1. Okay? So no matter how far we go out to the right, is that behavior ever going to change? Because think about it, no matter how many times we go around the circle, do the values ever change? Never change. Okay? All right, let's take a look at the cosine function next. If we were to do the same thing here with cosine, let's start out with the cosine of 0. Zoom back out a second. If we start out with 0 again, what's the cosine value here if we're at this point? It's the x-coordinate of this point, which is 1. Okay. And then if we do the same thing, we'll do the same points here. We know that that's radical 2 over 2 still. We know that pi over 2 this time would be 0, because at the top, the x-coordinate is 0. Okay. And then we go 3 pi over 4. Radical 2 over 2, or excuse me, negative radical 2 over 2, that is. Keep in mind it's negative radical 2 over 2, because we're over here, second quadrant. You told me cosine was negative, remember? This is the x-coordinate. And then finally, pi, we're at negative 1. So let's plot those points and see what we get here. So we got 0, 1. We have, again, I'll keep my tick marks the same on this. We have pi over 4, radical 2 over 2. We have pi over 2, 0. We have 3 pi over 4, radical 2 over 2, negative. And so ultimately our shape looks like this. Okay. And if we were to continue to plot, it would go up to 3 pi over 2. And then finally it would go back up to 2 pi right here. And once we get to that 2 pi, what's going to happen? Start over. Okay. All right. Notice how this jives with what we said about the unit circle too here, because remember, between 0 and pi over 2, thinking of your unit circle, wouldn't that be what our first quadrant values are? First quadrant values are positive, so our function is positive. As we go from pi over 2 to pi, which would be these values, they're negative. Pi to 3 pi over 2, they're also negative. So notice that it stays negative underneath the whole entire time between pi and 3 pi over 2. And then once we get to 3 pi over 2, then the x-coordinates become what? They become positive again. Okay, so is it surprising that the curves look like that? Based on the fact that we know they're defined by the unit circle? Good. Okay, questions so far? All right, if you look on page 386, there's also a yellow box with our cosine function facts in there, and you'll notice that the facts are almost exclusively the same as for the sine. Okay. Except for the symmetry part, it's symmetric over the y-axis this time, so that makes it an even function, which means that if you put in cosine of negative x, you should get the cosine of x. Remember, if you get the same thing back when you put in negative x. And then, looking at these two functions together, notice that they have almost the same shape, don't they? Matter of fact, if I were to continue this over here, okay, and look at the cosine, just for that part right there, doesn't that look like exactly the same picture as I drew above? So if you think about it, what are the sine and cosine to each other in terms of what we know about translations? Not inverses. Good guess, though. In terms of translations. How do these compare to each other in terms of translations? Oh,
The cosine is 2 to the left of the sine.
2 tick marks, which for us would be pi over 2. Okay. So the cosine is pi over 2 to the left of what the sine is, isn't it? Or could you say it the other way and say the sine is pi over 2 to the right of what the cosine is? Okay. And actually, thinking a little bit more out of the box here, couldn't we say that the cosine is 3 pi over 2 to the left? So think about it, if I move that a whole another 2 pi or whatever, okay, we could really say there's really an infinite amount of ways we could say this translation, could we? The easiest one obviously would be the shortest one, which is the pi over 2. Okay? So ultimately the sine and cosine, okay, are just translations of each other. Okay? One's a one, if we consider the sine one starting at the origin, we would consider this to be moved over pi over 2 to the left. Okay? Or like I said, if we're considering the cosine, we could think of that sine as the cosine but moved pi over 2 to the right.